Yes, so we are back into the beams, and what we did in the last class is what I was talking about. So in the last class, we learned few things. One is we developed a relationship between curvature and strain relationship, right? That is what we developed. Second, what we developed is curvature and stress relation. We are yet to relate stresses and strains with the external loading or external bending moment. We have not yet gone into that. Probably today we will get into this. Also, what we learned, a few things we learned about neutral axis. We still don't know how to find them, but we've learned about its definition is learned, right? And its usefulness is also learned. Okay, so what we did to find curvature. So curvature is what? So if you have a beam, okay, a cantilever beam, let's say, and this is the elastic line. This is called elastic line. What is elastic line? Why it's called elastic line? It is called elastic line because the line is deformed assuming within elastic limit, okay? Which one is the elastic line? Generally, the central line or the central axis or the neutral axis of a beam is called elastic line, okay? So this might be the beam. Okay? The center line is called the elastic line. Now, if you give some load on the beam like this, moment M, okay? So pure bending case, right? This is a pure bending case. So 0.1, a pure bending case considered. And then what you do is you see that the beam bends, right? So the beam bends something like this. All right. No, drawing is not exactly correct because the length has increased. It will not have an increased length, something like this. Right. So, oh no, what? Let me do a few things here. One is let me pull it back down a little bit. Okay. All right. And this can go here. Point number 4, as a point number 4. Okay. Now what you do, since plane sections remain plane, okay, next point is plane sections we cannot do anymore here. So 5 point. Plane sections or no, lines normal to the neutral axis, right, remain normal before and after bending. Okay. So if I had considered two lines which were something like this, let's say, normal here, they will stay normal here also, something like this. Now, since this is the curvature, and they are now normal to this curvature, so they will be inclined, right? And since they're inclined, they will come and join at some point. Let's say that point is O. Okay. So I'll write that also here. 6 points, since pure bending, the beam will form a circle while bending. The handwriting is not very good today because I'm in a constrained way I'm writing, because if I move a little bit, the connection is losing. Oh, it's a very loose connection in my office. I don't know why. The iPad doesn't want to connect. Anyway, right. So that's the concern. So if that is my rho, if this is my rho, the radius of curvature to the neutral axis. Okay. What is rho? Rho is radius of curvature to the neutral axis, right? Okay, and if that is dx, in a curved space, it will be ds. Okay, so and if this angle is theta, d theta, the angle subtended is d theta, then we get a relationship as we discussed in the last class. The relationship is kappa and strain. Not yet strain. Okay, let's say dx, length, element is, how do you write it? Then we write it as rho d theta is equal to ds, which can be approximated as dx. That gives me d theta by ds is, or approximately d theta by dx is equal to 1 by rho, which is curvature kappa. All right, we get this relation, but this relation still doesn't relate to my strain because the neutral axis is not extending, right? So since the neutral axis is neither extending nor contracting, I cannot relate it with the strain. The strain at neutral axis is 0. So what we do? We now look at the beam in more details. In particular, we assume the beam to be now of a curved format, right? Let's say this is the bent portion of the beam. Okay, we have not drawn a simply supported beam. That's not a good idea to draw it here. You will get confused when you see it later. So let's say we have the beam like this. Right? That's my neutral axis. And that's the depth of the beam. Now you take 2 points, 2 points. Let's say I take 2 points here. And they are connected to this line and connected to this line, right? So this line is obviously have got contracted because it is on the upper side for a sagging moment. So this is sagging, okay, positive moment. Positive bending, which is called sagging moment, right? Sagging. So obviously this is going to get contracted, right? And its original length was, its original length was this length, right? Because this is the neutral axis length. So let's say that is dx. Okay, all right. So, and this portion is y, because neutral axis y is 0 at neutral axis. Y equal to 0 at neutral axis. Okay, so any point above neutral axis at a distance y, right, along y-axis, we can find its, changed length. Let's say that is dx dash. Dash is not a good way of writing, right? So how do you write it? Let's write it as dx1. Okay, so now what is dx1? So dx is equal to rho d theta, and dx1 is equal to rho minus y into d theta. Therefore, change in length by length, change in length by original length is equal to dx1 minus dx by dx, which is going to come out as minus y, I think by rho, right? Did I write it correctly? Yeah, supposed to be that. And how do I come there? We have missed one step here. The other step is going to be rho d theta minus y d theta minus rho d theta by rho d theta, right? So this rho d theta and rho d theta cancels. It becomes minus y by rho, and which is equal to minus kappa into y, right? Minus sign, negative sign is due to compression, okay? So towards the bottom of the neutral axis, therefore, for sagging moment or positive, okay, the strain is positive below neutral axis and negative above axis. So this line is particularly a good choice for an objective question. Okay. All right. So having said that, so we found strain. Therefore, epsilon xx is equal to minus kappa into what? How to find stress? So from here we can find stress, right? So therefore, sigma xx is going to be E into epsilon xx, right? And that's going to be minus kappa E into epsilon xx. This is what we learned in the last class. Now to find, let me take again here. This should be y. Right? Now to calculate y, we need to know neutral axis, right? Y is calculated from neutral axis, positive upward. All right. Now, if I do that, how do I find neutral axis? That's my first question going to be that we need to answer. How do we calculate neutral axis? Because once we calculate neutral axis, we know that's my zero line of y. So that is the zero axis of y. And above that, I'll calculate positive y. And therefore, I can find stresses and strains. And below that, I'll calculate negative y. And therefore, I can calculate stresses and strains as positive. So if you put negative y here, something around minus 10, then it becomes positive here, right? So that's tensile. So, but to do that, I need to know my neutral axis. And here is how you have to find neutral axis. Right? If you remember that what we said in the last class, that I'm going a little slow in beams because the understanding of beams is very, very important. Okay. So I'm going a little bit slow, but we'll catch up. No worries. Now, what we said in few class before that, if you have a section like this, and there is a neutral axis here, right? I don't know, did I draw it correctly? This is not the way you represent. You represent as this cutout section. So if you have something like that, and then, there is this width of the beam. Okay. So E is your neutral plane. All right. And I said that there will be positives, there will be negative stress, that means compression towards the top. So towards the top, there will be compression. So if I draw this line here, up to this probably, yeah, and up to this here, right? Not fully. So it's going to be compression. So this is my neutral axis. It's going to be compression to the top and tensile to the bottom, right? So the stresses here are in arrow of this side because it is tensile, and the stresses here is of the arrow of compression, that means opposite side, right? But what I said, that since there is no axial force acting on the beam, right? Since there is no axial force on the beam at that cross section, we will have FH should be equal to 0, right? Right? That's what we said, right? We said that if you calculate all the loads here and it goes through L by 3 here, and that is called FC. And if you calculate all the loads here and that goes through here, that is called FT, then FC plus FT is going to be equal to 0, right? Now, how do you calculate FC? You calculate FC above the neutral axis and you calculate FT below the neutral axis, right? The summation of all the forces about neutral axis is going to be equal to 0. So that if I do, this is how I have to write it, right? These calculations I've shown in a few classes before. So you assume a point here on the cross section. So this is the cross section. So this is this part. Okay. This is actually this part. It can be rectangular, it can be any shape. So there is another shape that has been considered here. So if you consider this shape, right, you consider a small point here, right? So in that small point, there is a stress that is acting. So this is, since this is upper side of the neutral axis, the stress is going towards the plane of the tablet. So it's going inside, right? So the force on this is along this direction. So it will be higher along this direction and lowered here, right? Something like that it will go. Something like that. So if you consider a small point here, right, we can say there is a sigma acting at that point. This is the small point here. Now, if I integrate that point, or if I integrate that force over the whole area of the cross section, I will get the total force acting on the system, and the total force at that cross section, horizontal direction forces, right? Horizontal direction force at that cross section is going to be equal to 0. So I can write this very well as sigma x dA. Sigma x is the load that is acting there, the stress that is acting there. Sigma x dA integrated over the whole area, cross sectional area. Remember, cross sectional area is going to be equal to 0. Now I know sigma x. Sigma x is epsilon kappa y with a minus sign, right? This is my sigma x. I've just derived it. Sigma x is epsilon kappa y with a negative sign. Integral of that is going to be equal to 0. So negative sign doesn't matter, goes out. E is constant, right? Kappa is constant for that cross section, right? So we said that. So we'll write it again here. 1 point, E is constant. Assumed made of same material. And then 2 is kappa is constant for a cross section. Now, where are these not? So that leads to, okay, I'll come to that. That leads to that integral over the area y dA equal to 0. And that's actually your equation for neutral axis. Okay, equation to find neutral axis. All right. before you ask any question, let me ask you a question here. I have given two assumptions here. These assumptions are over and above all the assumptions that we made before. Okay, that is plane section remain planes, normals remain normal. Okay, straight line remains straight line, and the homogeneous material, isotropic material, all these within elastic limit, all this, given above that, for this formula that I've derived, I have two more. One is E is constant along the cross section. Two, kappa is constant along the cross section. Why I said along the cross section? Because I am dealing with only one cross section, right? The relationship will be valid for the next cross section also, but the values may change. E may change, kappa may change. Now you tell me under what conditions these two assumptions will not be valid.
Sir?
Yes?
A small doubt, sir. Sir, here kappa is just 1 by the radius of curvature, sir. Like 1 by radius of curvature. Right? So why would it change there? Because for a beam, when it is bending, like it should remain constant always. Sir.
No, if the moment changes suddenly, it will change. It will depend on bending moment. Okay. If
does
a
it mean
cross
moment
section has
changing with time, sir?
moment can change with time, moment can change with loading also, right? So for example, I gave only one moment here, right? In this beam, I have given only one side moment here. If I give another moment here, the curvature will change. Curvature will be like this and then this.
Yes, sir, but even then we will be calculating that for that particular instrument, so for the given moment, anyways, those will be wrong.
Not for a given moment. You have to calculate based on the bending moment in the material, in the beam structure. Now, if the bending moment changes, then kappa will change at every cross section, right? Kappa will not change in a cross section. For a cross section, it is constant. That's what I written here. For a cross section, kappa is constant. For the next cross section, it will depend on the next bending moment. So kappa can also be a function of x if Bm is a function of x. Okay. E can be a function of x if your beam is made up of different materials. But for a given cross section, E and kappa are assumed to be constant here. My question is, for a given cross section, under what conditions we will not have E and kappa to be constant? You understood? Right. The question is not along x. Along x, your kappa and E both can change based on the materials that you have, based on bending moment that you have, right? But given a cross section, that means given an x value, can E and kappa change? I have assumed them to be constant. My question to all of you, can they change? If they change, under what conditions will they change?
Sir, are we still under the elastic limit?
We are still under elastic limit, yes. So in the plastic limit, things are different. So let's not go into that. E value can change in plastic.
There is a composite material.
E, which one will change?
E.
E will change if this is made up of composite material. Yes. There will be E1, E2, E3, all these things can come. So E can change. So you cannot take E as constant in that case. Okay. So that rule, YdA equal to 0 will not hold if you have a composite material. In that case, E will not come out of the integration sign and you cannot put it to 0. Ganesh is also right, but not fully. If it's not a pure bending case, kappa will not. So in case of with shear stresses, if the shear stresses are very small, kappa still remain constant. But remember, kappa to be constant, we need to have this straight line to remain straight line. Remember, if the straight line is not straight line, then kappa is not constant. And for that, I have given you a figure. So relate with that figure. Where is that figure? Yeah, here. Right? If it is like this, your kappa is not going to be constant. And under what condition it is not like that, not like a straight line, but like this? Under large shear stresses. Okay? When you have deep beams, right? In that case, you cannot use this. Okay, so these are primarily candidate for objective questions. All right. Okay, so now we have learned how to calculate neutral axis, right? So next is let us go and relate moment, external bending moment or bending moment in the beam with the stresses, right? Because that's what you know. You will know bending moment. right? From the given loading, you can calculate bending moment and shear force, but we have to finally calculate stresses. We have not yet done it. Let us do it.
Sir,
Yes.
sir, you said for the planes to remain parallel, we should have small values of stresses, right?
Small values of shear stresses.
Yes, yes. So now, like technically, if we are still under the elastic limit, wouldn't that be already taken care of?
No. Within elastic limit also we can have shear stresses, no?
Yes, sir. But even the shear stress should follow that relation for like the Hooke's law, right? Like we should have tau equal to g gamma. So that should also follow, right?
That will also follow, but this has nothing to do with linearity. That straight line that I said that normal to the axis will remain normal has nothing to do with linearity. Okay. That has to do with shear stress and bending stress. Now, when you have large shear stress, that line will not remain straight line even within elastic limit. Okay. When I say large, we will show you later that if your shear strain contribution is like 5% of the total strain energy that you have, then these are straight lines. But if it goes beyond 10, 15, your shear stresses, then the straight lines will not remain straight lines. They will start a little bit curving. Okay. And in those cases, we cannot use this relationship that we have. We can use, but it will give you erroneous results. Your results will be that much approximated. Okay. Let me finish, then I can show you something. Yeah.
Hello, sir.
Yeah. Irish.
Sir, please go page up. No, the about two formulas FC and FT. No, yes, this. How did we calculate? Means I'm not
Which
getting.
one?
The first two lines above the bar chain.
This is very simple. See, this is a triangular load, right? Right. So total force acting is how much? Sigma max into half into this distance C1. Half into C1 into
Oh,
sigma
okay,
C1.
okay. So for this only, na? Okay.
For this one.
I thought
And
it
that will be
was
multiplied. Yeah, that will be multiplied with B, of course. I have missed out
yes, yes.
B. That will be multiplied with B, of course. The
Okay,
B.
okay.
Actually, you have to integrate it. If you have a section which is like this complicated, you actually have to integrate it. Right? So if you assume it to be rectangular cross section, then you multiply with B. So this is not necessary to calculate. This formula is important. Now, if we have to calculate with the moment, right? We have to relate with the moment. So now we know that the force generated by this small section here, same section, if I take same cross element, then the force is sigma x into dA, right? The moment will be generated about to be neutral axis will be sigma x into dA into y, right? So sigma x into y into dA, and that is negative sign will come because it's compressive, right? So that is your differential moment that is generated by this element. Now the total moment that will be generated is integral over the area A sigma x into y dA, right? So total moment will be integral over this. Total moment. Okay. Now we know I can replace sigma x with kappa, right? A epsilon y, right? If I replace that with this, then it becomes kappa into E, y into y will become y squared dA. And this my negative sign and that negative sign will cancel. So it becomes integral over A kappa E y squared dA. Now kappa is a constant for a cross section. We just discussed. E is a constant for a cross section. We also discussed that. So if that two comes out, it becomes integral over A of y squared dA. Now y squared dA integral A is, we all know, it's what? It's a moment of area, second moment of area of the material. So if you take this is the second moment of area and we represent that as I, we get M equal to kappa EI. This is called flexural relation. It's called the flexural relation, okay? And then we can write M is equal to sigma x, yes. So kappa can be written as now sigma x by EY. Why is this? Yeah, this comes from here and kappa is sigma x by EY, right? And then this E and this E will cancel. Then you become sigma x is equal to M by I into Y. This is called flexural relation and this is very important. Flexure formula. This is very important and you have to remember this. Sigma x is m by I into y, right? So you can see that m is a constant at a cross section, bending moment is going to be constant. I is a constant at a cross section. So it varies with y, therefore it varies linearly with y. We have discussed this earlier, strain varies linearly. So it's going to vary like this linearly with respect to y. Okay, and I, if you have to be very careful with I, we generally write it as I, but it has to be written as I z z because this I is about this z z axis, right? Okay, so we write, it's better for you in the beginning to write it as about I z z axis because the bending is taking place about this. The moment is here about this y axis, about the z axis, right? So this is my z axis, and the moment is here. And therefore, the bending will take place about this axis, and therefore it's written as IZZ axis. Just to make sure that you understand that, so if you have a cross section which is rectangular here, you will have two lines, right? This is one x-axis, z-axis, and there is one y-axis in the cross section, and the x-axis is along the length. Now you can have two I. One is IZZ, this is red one, and one is IYY, which is this black one. When your system is in plane bending, again the same thing coming. When it is in plane bending, you have to take IZZ. When it is out of plane bending, you have to take IYY. Or if it's both of them combined, then you have to take both of them and do your calculation properly. We will do it later for unsymmetric bendings. But right now, for symmetric bending, my beam can bend in both directions. Right? So if MZZ, then you have to take IZZ. If it's MY, then you have to take IY. Okay? Is that clear? So that's very important. Yeah, Kanika, so just a minute. No, let me finish this. Okay, so M is bending moment. So be careful. It's not external moment. It's bending moment at the cross section. Y is different from neutral axis. Distance from I is moment of inertia, and you have to wisely choose your IXX or IZZ or IYY. Okay, most of the sections will be given to you, and its I will also be given to you. Okay, so I'll stop here and would like to. This is an important formula. You know, this is a very important formula, and you have to remember this formula. Sigma by y equal to m by I equal to E by rho. This relates all the relationships, all the formulas that we have developed till now are all in this. All the formulas are here. Okay, so this, if you remember, you can relate all the formulas that we've done before. Okay.